Okay, now it's time to do some practice. We're going to do practicing with the squeeze theorem and also with our favorite limit of the day. Sine x over x, sine theta over theta, whatever you like to call it. Sine of blah over blah. It's a really important limit. We're going to have frequent need of it in the next couple of weeks because we're going to keep coming back to it again and again. Now, when you're doing these problems, make sure to use the frequent use of that pause button. Try to do as much of these problems as you can on your own and only look at the solutions when either you're stuck and you can't make any progress, or once you've seen the answer, just to verify you did things correctly, or maybe get a different perspective on how to do things. All right, let's get into it. So our first problem, find the limit as x goes to 0 of x times sine of 1 over x. Now, let's be careful here. You might be thinking, oh, maybe this is our sine x over x. No, that's coming later. Let's recall something. So previously, we actually saw this sine 1 over x curve. We know what it does. So sine of 1 over x has sort of this strange phenomenon where it's coming in and then it starts to oscillate up and down infinitely often, and it's not defined at 0, and then it does something similar on the other side where it oscillates up and down infinitely often. And so if you only have sine of 1 over x, it doesn't have a limit. The limit doesn't exist at 0. But we don't just have sine 1 over x. See, we have a little bit of help now. We have that. Now you might be thinking, okay, it's an x. What is that? Well, the reason that that's helpful is really what we have going on here is we have two pieces. So x sine 1 over x. And the key here is the x part. X is going to 0. So this is going to get small. All right, so that's useful to know. But there's a second important thing to see. What do we know about sine 1 over x? We know it's going up and down a lot. It oscillates infinitely often. But even though it's oscillating infinitely often, it doesn't get very big or very small. It's always between -1 and 1. So here's where the squeeze principle comes in really well. If you have two pieces and you say, oh, there's this terrible looking part here. It's ugly. I can't control it. It's wildly fluctuating, but it's bounded. And then there's this part here saying, and it's getting small. If you combine these two together, the net result is that it has to be small. Small times bounded goes to small. It's when you have something small times something which is bigger and bigger and bigger, you get problems. We'll be talking about that at some point in the future. But okay, so how do we make this now rigorous? Well, now we say, well, look, the real problem is the sine 1 over x. But because I know that sine of 1 over x is between +1 and -1, what does that tell me about x times sine 1 over x? Well, now if x, okay, I'm going to be a little bit cautious here. You might want to say, hey, let's just multiply everything by x. And that would be okay as long as what was true? As long as x was positive. See, if x is positive, yeah, I can multiply everything by x and I preserve the inequalities. So it's true that for x, which is greater than 0, I'm not going to worry about x equals 0 because this is undefined at 0. You can't plug 1 over 0 in. It's like infinity. I know people think of that. It's kind of like infinity. It doesn't make sense. We have that negative x is less than or equal to x sine 1 over x is less than or equal to positive x. Now, what happens for x less than 0? Well, if x is less than 0, what ends up happening is you flip the inequalities. Because when you multiply by negative, your inequalities go in the opposite direction. So what you have is that for x less than 0, you have what? Well, it's still negative x greater than or equal to x sine 1 over x is greater than or equal to x. Because you, again, multiply by negative, flip the inequalities. If you combine these together, there's really a very simple way to say this. So what you can say is that x sine 1 over x is below what we call absolute value of x and greater than or equal to negative absolute value of x. All right, good. Now, let's draw ourselves a picture. So what we have is we have the following. When we draw our axes, we have the bounding curve on the top is something very nice. Absolute value of x is a very nice function to work with. It looks like a v. So there we go. Negative absolute value of x is similar. It also looks like a v, but it's upside down. So it looks like that. And now what we know is that our function x sine 1 over x is going to be somewhere in between. So I'm in between these two. Now I don't know exactly what it looks like for right now. We'll get a better sketch in a second here, but that's what's happening. Now, our curve, x sine 1 over x, has to be on the inside. You can already see the answer, right? Because what's happening? What's happening is that we're being squeezed in. We're getting squish, and we'll see the answer already. We'll go ahead and write it down. 0, right? Because what's happening is as I come in, I'm going to be basically bouncing back and forth. So see how I'm bouncing between -1 and +1 here? Now I'm bouncing between these two curves. And I'm going to bounce infinitely often, but even though I'm bouncing infinitely often, the amount of bouncing I do is getting smaller and smaller and smaller, and I'm going towards 0. So the limit is 0. So this is an example of using the squeeze principle, and the key is to say, what is something which I can bound below, what is something I can bound above, and put those pieces of information together and get what I need. All right. Now, let's do another problem. Find the following. So we have some really simple looking limits here. Limit as x goes to 0 from above of absolute value of x over x. Limit as x goes to 0 from below of absolute value of x over x. And simply the limit as x goes to 0 of absolute value of x over x. So what do we do here? Well, let's just take these one at a time. If I'm coming from 0 from above, the nice thing about absolute value is that it changes its behavior at 0. So if I'm coming from 0 from the above, so here's 0, and I'm coming in from above. What's true? Well, what's true is that the absolute value of my function, absolute value of x, is x, because when I have a positive number, the absolute value doesn't change it. So because I'm coming from above, this is really the same as the limit as x goes to 0 from above of x over x, because I can drop the absolute value, because I'm using my assumption I'm always above 0. Also known as the limit as x goes to 0 from above of 1. Well, that's a nice limit. We know how to take that limit. It's 1. And that's our answer. Okay, well, that's the first one. Let's do our second one. So, our second one. Now, what's happening here? So I have 0 again, and I'm coming from below, right? From below. Now, if I come from below, what's happening? Well, what happens is that absolute value of x will change the sign. So, what I can say is that this is limit as x goes to 0 from below of negative x over x, which is the limit as x goes to 0 from below of -1, which is -1, because limits of constants are the constant. All right. Now, the question, what if I'm coming from both sides simultaneously? What's the answer? Well, we saw when we were coming from above, we were going towards 1. When we were coming from below, we go towards -1. Well, what do you notice about these two things? They're not the same. There's a gap. And when there's a gap, what does that tell us? It tells us because they do not agree, that this limit does not exist. They have to agree. All right, so this is one of the things that we oftentimes do. Why do we do this from above and from below? Really what we're seeing here, what's being reflected, is the fact that absolute value is what we like to think of as a piecewise function. So we oftentimes think of the absolute value of x as being x if x is above 0 and negative x if we're below 0. Now you might say, wait a second, you put 0 in both categories. Well, it turns out that 0 and negative 0 are equal to each other. True fact, true fact. And so this is a natural place to use a natural place to use one-sided limits because we have a piecewise function. All right, good. Well, speaking of piecewise functions, let's do another problem that involves piecewise functions. So we're given a function, and it's defined piecewise. It's 1 if we're less than or equal to 0. It's x squared if we're strictly between 0 and 1. It's 2 if we're equal to 1. And it's 2 minus x if we're above 1. Okay, so let's think about this. Now, one way to do this is we can do it using the algebra. Another way is we can sketch a picture and see if that's good enough. Now, let's sketch a picture really quickly, because this is not such a hard function, I think, to sketch. So it's 1 if we're below 0. So let's say, let me change my color really quickly. Okay, so here's 0, I'm at 1, and notice I'm full circle because I'm including it, and then I'm a constant 1. Then it switches to x squared between 0 and 1. So that's a parabola, open circle, don't include it, going up, and there's an open circle here. Now at 1, it's the value 2. So here's 2. Now, if we're above 1, what do we have? Well, it's 2 minus x. Now, 2 minus x is a line. It intersects here at 2, comes down. Now, notice I'm not drawing anything because I only draw the part that's above 1. Once I hit 1, which is here, well, it turns out 2 minus 1 is 1. And now I start drawing. It's a line with a slope of negative 1. So that's what our function looks like. Okay, so now we can start talking about our various pieces. So what's the limit as x goes to 0 from below of f of x? Well, from the picture, we see, aha, it's following this straight line, it's 1. Algebra would say, well, if I'm below 0, what I do is I cover up the rest of this, and it kind of washes out here in the image, but I cover up the bottom parts, and I say I only focus on this part right here. So the limit as x goes to 0 from below of f of x is 1. How about the limit as x goes to 0 from above? Now, notice that there's several things which are above 0. X squared is above 0. 2 is, because I'm between 0 and 1. This value for 2, 1, that's above 0. If I'm bigger than 1, I'm certainly bigger than 0. Which piece do I need? Which one of these three parts do I care about? The answer is, when we're taking limits, we care about what's happening nearby. We don't care what happens far away. And far away is any measurable amount. So I don't really care about this 2 minus x. I don't care about this 2. I care about the x squared, because that's the behavior nearby 0. So when I look at this, I say, well, the x squared, what's it doing as I come in towards 0 from above? The answer is it's approaching 0. So that's 0. Now, notice that what we can do is we can combine these, and we can say that the limit as x goes to 0 of f of x does not exist. Now, it didn't ask us to say that, but we could. Why not? Extra knowledge, right? All right. Now, if you're on a test, don't do more than what the question asks. But, it's always fun to know more. Knowing stuff is good. All right. Now, how about 1? So as I approach 1 from below, well, the question is, what's just below 1? What's just below 1 is that part of the parabola x squared. And the behavior is it's approaching 1. So it's 1. So really, let me just go ahead and spell out why we want to do piecewise functions this way. When I'm approaching 1 from below, so I'm just below 1, I come here and I say, well, that means I need to follow the x squared pattern. So I replace f of x by x squared. And now I have a function I can work with, a polynomial I can work with. And that says we know polynomials, no surprises, we get 1 out. When I'm approaching 1 from above, I'm going to use the part that's just above 1, which is the function 2 minus x. So I can replace that, f of x, by something which I know how to work with. 2 minus x is a polynomial, plug in 1, 2 minus 1 is 1, and now, lo and behold, we can say, aha, the limit as x approaches 1 of f of x is 1. So that limit does exist because the limits from both sides agree. Now, you might notice, of course, that you have this strange behavior. So this is saying that, look, what happens at 1 is different from what should happen at 1. Because remember, limits are what should happen. The function is what does happen. They don't always have to be the same. All right, good. Well, now let's dip our toes into some trig. Find the limit as theta goes to 0, 1 minus cosine theta over theta. Now, when you see something where I have an expression where there's a trigonometry part, that's cosine, and there's what I call an algebra part, that's theta. So in other words, like a polynomial, or maybe like a square root or something. When you see these things combined, trigonometry and polynomials or algebra, you start thinking in the back of your head, there's a bridge. There's something which connects these together. And the thing which connects these together is you say, all right, the key fact is limit as theta goes to 0 of sine theta over theta is 1. So what we need to do now is ask ourselves the question, can we get to something that looks like sine theta over theta? And how do we get there? So we start rummaging through our mind. Well, I see a cosine, and I think about all the identities that we have in trig, where there's a cosine and a sine simultaneously in the identities. Now, there aren't that many identities which are useful to know. In fact, there's only about a half dozen that you really need to know. And among the half dozen, there's one that rises above them all. And the important identity is that sine squared plus cosine squared equals 1. So we say, aha, if we could replace our cosine by sine, one way we could do it is get a cosine squared. Well, we don't have a cosine squared. We only have a cosine. I guess I should have paused for a second and said, before we even went down this route, do we need to do anything? We should suspect that we have to do something because, we don't do things just for fun. Why do I say we should suspect we have to do something? When you plug in 0, downstairs you get 0. And that's usually when you get a 0 in the denominator. It's oftentimes a sign more work lies ahead. Upstairs, you get 1 minus 1 because cosine of 0 is 1. So you really get 0 over 0. So there really is, in fact, more work to be done. All right. So that's why we are doing more work. Okay. Now we have to think, how do we get a cosine squared? Well, what we do is we employ one of our good tools. Well, we have lots of good tools because we know things. Knowing things is good. But in this case, our good tool is if you want to start squaring things, we use the conjugate. So oftentimes you think of like the conjugate is to get rid of square roots. In some sense, the conjugate is to get squares involved. So if I want to get a square here, I'll multiply by the conjugate both upstairs and downstairs. Now, if we do that, what do we end up with? Well, we get the limit as theta goes to 0, upstairs, 1 minus cosine squared theta, downstairs, because we span it out, a squared minus b squared. Downstairs, we are not going to expand. So we leave it as theta times 1 plus cosine theta. We only expand where it's helpful. If it's not helpful, we don't do it. Now you might say, but Steve, you still got a cosine theta here. How are you going to get rid of that? And in some sense, I'm going to say, I'm not going to worry about that cosine. Well, what's the difference? Well, the difference is, here when I plug in 0, what do you get? 1 plus 1. 2. I like 2. 2 is a great number. But before we had 1 minus 1, 0. That's a challenge. We've got to deal with the zeros. All right, so we're okay with that 1 plus cosine hanging out. 1 minus cosine squared, sine squared. All right, so this is the limit. As theta goes to 0, sine squared of theta divided by theta times 1 plus cosine theta. Now, what we're going to do is we're going to say, let's break things up. I know something about sine theta over theta, and I now see a sine theta upstairs and a theta downstairs. So we're going to write this as the limit. Theta goes to 0, sine theta over theta, and everything else. So now we've really broken it, and we said, look, let's separate it out. And we're separating it in such a way where we understand both the pieces. So sine theta over theta, that we now know goes to 1. And that's a great thing because we're handling a 0 over 0. By using our fact, we're able to say, hey, I've handled a 0 over 0. And I figured out that that part goes to 1. Now the question is, what happens here? If I get a number, that means I'm done. Oh, number. Come on, number. Well, plug in. Sine of 0, 0, good sign. 1 plus 1 is 2. So this goes to 0 over 2. And 0 upstairs is okay. It's 0 downstairs where you have to panic. So we now say, okay, both pieces have limits. So the answer is what you get when you multiply those together. 1 times 0, which is 0. Very small. This is an important limit. We're actually going to come back and use this one in a future session. So don't forget about this one. Now, 0, not too satisfying. Let's kick it up a notch. Well, what's our kick it up a notch? Let's do the limit of 1 minus cosine theta over theta squared. All right, now, because we've already done some work, we can say, look, we know the idea. Multiply by the conjugate. Replace the 1 minus cosine squared by sine squared. So I'm going to go ahead and just say, we know how to do that part. So multiplying by the conjugate and simplifying. And so I'm going to skip a step or two here. I'm going to use the infamous ... Always a little bit dangerous. It means, well, there's some intermediate work, but you know what it is. Okay, limit theta goes to 0, and we got down to sine squared upstairs, theta squared downstairs, and a 1 plus cosine theta downstairs. Well, let's do a similar thing. Namely, let's break it up into pieces where each piece is easy for us to understand. So we have, I'll break off a sine theta and a theta. I'll break off another sine theta and a theta. And finally, well, I've used up the upstairs, so I'll have it as a 1. Downstairs, I've grabbed both of the thetas, so I'm left with 1 plus cosine theta. Well, what did our pieces do? Sine theta over theta goes to 1. Sine theta over theta still goes to 1. 1 over 1 plus cosine theta goes to 1 over 1 plus 1, also known as a half. So our answer is 1 times 1 times a half, and so we get a nice number, a half. Now that's kind of interesting. Now, let me point something out, because I think this is kind of fun. And it may not be immediately obvious that we've actually done this. So let's go ahead and actually see. Aha, we can say something cool here. Remember what limits tell us. Limits tell us what's happening nearby. So what we can say is that near 0, this expression of 1 minus cosine theta over theta squared is near a half. So near 0, we'll go ahead and write that out. We get 1 minus cosine theta over theta squared is equal to a half. Or we could say 1 minus cosine theta is a half theta squared. And now if you just swap these two, we come to the conclusion that cosine theta, and I shouldn't say equals, I should say is approximately. It's not that it's exactly equal, but it's approximately. So cosine theta is approximately 1 minus a half theta squared. So that tells you, if you draw the cosine function, and the cosine function looks like this, that near 0, that it's mimicking an upside down parabola. And so near 0, and it doesn't, it goes away, and it's not exactly the same, but it's close. That's the key idea, is that it's close. Now, that doesn't seem like it was too much work. I will say, for your friends who might be in Calc 2 right now, near the end of Calc 2, they're putting in some effort to get to this. And we got it almost as a freebie. Of course, they're going to go a little bit further and say, hey, I can get even better and better. Well, there's a great story to be told there. But that's a story for Calc 2. We'll get there. We'll get there. Hang in there, my friends. Okay, so let's do another problem. Oh, who would have guessed? More problems. Well, there's always more problems. Okay, find the limit as t goes to 0, sine of 3t over sine of 4t. Now, there's two approaches. The first approach is to say, let me pull out my trig identities and rewrite sine of 3t and sine of 4t in some crazy way. Of course, you got to be really good with your trig identities and really patient, and fingers crossed something will cancel. Okay, that's an option. I'm not saying we're going to pursue that option, but that's an option. Option number 2 is to say, well, what do we know? Right now we can see that there's a problem. This is definitely a limit that has a problem. And why do I say that? Well, what is happening when you plug in 0? You should always check. Plug in 0 and see what you get. You'll get sine of 0 over sine of 0. Now sine of 0 over 0 is 0 over 0, which of course is the universal symbol for more work. It means we don't know what it is yet, but we will. We're going to figure this out. And now we start thinking, okay, well, what can we do? Well, the thing that might not be immediately obvious is to say, let's pull out one of the things that we know about sine. We know the following fact, and I'm going to write it in our strange way. Limit as blah goes to 0 of sine of blah over blah is 1. So in other words, if I have sine of something upstairs, something downstairs, I'm taking the limit as I'm going to 0, I'm going to go to 1. Now the something doesn't have to be x, it doesn't have to be theta, it just has to be consistent and it has to go to 0. Okay. Now, remember, that expression, that shows up as our bridge between trigonometry and algebra. And so you're probably thinking, but we don't need the bridge because there's only trigonometry. Why would you introduce this? Well, let's throw in some algebra. So let's throw things in. Okay, so here's our idea. We say to ourselves, let's look at this limit, and we're going to write it as sine of 3t, and give ourselves some very generous space here, and sine of 4t. Now, the thing is, it's a lot easier for us to manipulate algebra, so we want to rewrite this in a way that helps us get to a point where it's something we can work with algebraically. I know sine of blah over blah goes to 1. So I say to myself, well, right now, the blah, the inside, is 3t. If I could put a 3t here, then I've got my sine blah over blah. That part would go to 1, and life would be good. And you're probably thinking, well, life would be great if you could put a 3t there. But can we? Is that allowed? Do the rules allow us to put a 3t there? Well, the answer is we can put a 3t there if we balance it out. So the net effect is whatever we do, we have to have the total amount of change be 1. So if I'm dividing by 3t, I compensate simultaneously by multiplying by 3t. And you're like, oh yeah, the 3t's cancel. No, don't cancel them. We put them in there for a reason. Don't cancel those 3t's. Okay, all right. Now let's do the same thing downstairs. So downstairs, we're going to put a 4t, and then again multiply by 4t. We have to make sure that the expression that we end up with is equivalent to the expression we started with. Otherwise, we're not doing the problem, and we're not going to get the right answer. Because we were careful and we kept multiplying by 1, we're good to go. We can move forward. Progress, right? Now, what is our progress? Well, what we've done is we've said, we've got these pieces here. These pieces, the sine of 3t over 3t, sine of 4t over 4t, they're nice pieces in the sense that we understand their behavior. They're going to go towards 1. And now we said, okay, there's this other stuff here, which is algebra. We can do algebra-like things. So what can you do with the 3t over the 4t? Well, hopefully you can spot there's an easy thing you can do, which is cancel some t's. So we'll cancel the t's. And now we have a 3 over 4. That's actually a constant. And one of the things you can do with constants is you can pull them out of limits. So we have that this is equal to 3 over 4. Pull out the constant. The limit as t goes to 0. Upstairs, sine of 3t, divide by 3t. Downstairs, sine of 4t, divide by 4t. Now, we pull out our rule, and we say, you know, the upstairs, because the inside part, 3 times t goes to 0. And therefore, sine of 3t over 3t goes to 1, because it's sine of blah over blah. Sine of 4t over 4t, same process, because that 4t is going to 0, this whole expression goes to 1. So the limit is going to go to 1 over 1, which is 1. So our final answer is, this is 3 over 4. Good. And we're done. Now, one of the things you could have seen at the beginning, once you sort of get used to this thinking, you can say, well, how can I think of sine? Because we have our sine of x over x goes to 1 as x goes to 0, really what we can say is what that means is that near x equals 0, it's that sine of x over x is approximately 1. So another way to say that is that sine of x is approximately x. So if you graph the sine function, what you'll see is here's our sine function, nice up-down shape. And if you graph the line y equals x, they're very similar near 0. So what's the point here? Well, mentally, we can sort of get an eyeball of what should be happening. Since 3t and 4t are both near 0, well, we should say, well, sine of 3t is about 3t. Sine of 4t is about 4t. So it looks like 3t over 4t, which is 3 over 4. And that's the answer. Now, this part right here is making that slightly more rigorous, but you can start to sort of build up intuition. And once you build that intuition up, you're doing great. That's what we want. We want you to understand things. In fact, that's our preferred mode of operation, is for you to understand things and not just blindly run computations. It's fun to understand. Okay, one last problem for now, because I like doing picture problems. Here we go. Suppose that f of x is shown as in the figure below. So here we have this function. We don't know what the function explicitly is. So this is going to test our understanding. Can we figure out from a picture what's going on? And now there's a question. Find the limit as x goes to 0 of 1 plus f of 1 plus x over f of 1 minus x, or explain why the limit does not exist. So this looks interesting. Now, if you look at this, we can say that there's something strange going on. When we think about plugging in 0, well, we get 1 plus f of 1. But look, 1 is a really bad place here. it's not continuous. When you plug in 1, you get 2, but it's not the behavior coming in from the different sides. So 1 is sort of a wild west. It's saying this is not just going to be an obvious answer. So let's be careful, because we like being careful, right? Okay, so here we go. Here we go. All right, so we're going to do our limits. Now, when you have a function which is piecewise, in other words, it has different behaviors in different parts, one of the best things to do is do a one-sided limit. So let's try to tackle the question. What's happening as x goes to 0 from, say, we'll do it from below, of 1 plus f of 1 plus x and f of 1 minus x. Okay, so we need to ponder this for a second, and let's not rush. We want to make sure we get this right. So I know x is going to 0 from below, which means x is a little bit below 0. So we can think of it as a really tiny negative number. Okay, so that's how we should think of x. Very small negative number. So what's true about 1 plus x? Well, 1 plus x is a very, well, it's not a small number, but it's right near 1 on which side? Is it going to be below 1 or is it going to be above 1? Well, 1 plus a small negative number is below 1. So what's happening here is this 1 plus x, this part right here, this is approaching 1 from below, because I'm a little bit below. Now, what about 1 minus x? So 1 subtract a small negative number is the same as 1 plus a small positive number. So this part, we approach 1 from above. So that's how we should be thinking about what's happening to those little pieces. I'm either approaching 1 from below, or I'm approaching 1 from above. So what happens? Well, so let's take our function. As I'm approaching 1 from above for my function, I am doing what? I'm going in towards 1. So, whoops, I was pointing to that. I said above would be here. I'm approaching 1. There we go. I can see that. So this bottom part is approaching 1. How about the top part? 1 plus. Now, I'm approaching 1 from below. There's a negative 2. So 1 plus a negative 2. Well, so that says, okay, I know what the top is doing, I know what the bottom is doing. There's no division by 0. So 1 plus negative 2 over 1 gives me negative 1. Okay, all right. Now, that's from below. We're halfway done. Good. This is a problem so nice, we get to do it twice. We have to approach from both directions. X goes to 0 from above. 1 plus f of 1 plus x over f of 1 minus x. But same philosophy, right? I'm approaching 0 from above. So I'm coming in from above. What's true? Well, if I'm coming in from above, I'm really a small positive number. So 1 plus, this says we approach 1 from above, because I'm a little bit bigger than 1. And then the 1 minus, well, approach 1 from below. Okay. So we actually have done these similar computations before. We just now actually are a little bit careful. So what happens upstairs? Well, as I approach from above, I'm approaching 1, because this is from above. From above means from the right. From the right. From the right. As we approach it from the right, we get 1. So the top is going to 1 plus 1. How about downstairs? Okay, we're approaching 1 from below. So we're coming down this way, because when I say we're approaching 1 from below, really, keep in mind, what we mean is the input is coming to 1 from below. So the input, so we're moving along here. So that says we follow the function as we move along. We're going towards negative 2. So we have 1 plus 1 over negative 2, which is also known as negative 1. What do you notice about these two values? They're the same. So Now we say, when we approach from one side, we got -1. When we approach from the other side, we got -1. They match, and therefore our limit is -1. We're done. We're done. And I'll tell you, if you just sort of eyeballed it, I don't think it's so obvious that the answer should be -1. If anything, the answer should be like, it's not clear. But we do the work, and we can get a good answer. All right, good. Whew. That's a good round of practice.